Okay, so welcome to Project Darwin. I'll just start with or next slide, please. I'll just start with a brief overview of the problem we're investigating. So reinforcement learning applications are capable of solving many complex challenges with human performance. Problems in reinforcement learning are framed in terms of game-like constraints, where you reward or penalize certain actions, and then we introduce a model to learn an optimal set of actions when exploring the environment. Next slide, please. So since reinforcement learning agents learn in human-like ways, why not use them to simulate human-like challenges? Project Darwin's goal is to simulate an environment where agents living in the environment have to maintain health properties like rest and hunger so they can survive as long as possible. Next slide.
You're muted, I think, who is ever talking.
Sorry. So like the physical environment that our project is built upon, we used OpenAI Gym Mujolko, and basically it provides a simulation platform that allows us to define our learning agents, the available actions associated with the agents, what the agents are able to observe, are also known as the states of the agents. For example, the position velocity relative to each other, as well as the reward that directly controls the result of our algorithm. So as you can see from the pictures over here, the blue objects would represent our learning agents, and the green objects would be like our food. And then as the agent eats our food, it gains a reward. And the goal is simply just to maximize the reward of every agent. Next slide, please. Right. So in terms of the data collection and pre-processing process, because we build our own environment, so essentially we created our own data. So in terms of the pre-processing part, it's fairly straightforward. Basically for the states and observation, we just simply shape it into the appropriate format accepted by different, depending on our different neural network choices. And the rewards is the most important part here because it's used the model to define the loss function, and it's based on the time steps, agents, distance of food, and so on. Okay, next slide.
Yeah, so I'll talk a bit about our model. So in reinforcement learnings, each action of the agent is associated with the quality of the action, which we call the Q value. So this Q value kind of allows the agent to choose the best action at every step. Next slide, please. So with environments that are very large and complex, kind of like ours, you need to use a neural network to kind of take in the observation per agent and get an output of Q values, which is an approximation because we can't get an exact value. Next slide, please. So an improvement that we made was that we were allowing agents to kind of get information on how the other agents are doing as well. So we kind of lined those up, and we were able to use a convolutional layer previous to our fully connected layers to kind of improve our model. Next slide, please. So yeah, I'll share my screen. Yeah, so here you can see that, so our baseline environment, we're showing our baseline environment here. So we have two agents here moving around, and then the green dots here are the food. And you can see that in the beginning, they're kind of struggling to find where the food is at all. And then as it keeps training, it notices that the food actually goes inside the walls. So one of them just kind of happens to stumble upon the food. And then at the end, you can see that both agents kind of realize that food is inside the walls and go in to eat all the food. And so you can see here, it's like a loss plot for our baseline. And the oscillation is a very common thing in reinforcement learning model training. And then so we wanted to expand this idea to 4 agents. So we kind of wanted to see like if they would compete against each other. So at the beginning of the training, they're all, as usual, they're struggling. But then as we continue, a couple of them start realizing that food is inside the walls. And then towards the end, you can see a really interesting phenomenon where 3 agents here are really struggling to get in because they all want to get in. And then the other one comes and eats all the food.
Right, okay. So then a more complicated environment that we applied the algorithm to is called the survival environment. So as you can see in the video, the red dots represent this what we call the sleep sites, and the agent can gain reward when it's around the sleep sites and when it's eat the food. So we want to find a balance between agent sleeping and agent going to explore and eat the food. And the higher health the agent has, the more reward it will get. Go to the bottom, please. So as you can see, like once we're able to keep training, the what we end up having is our agents will spend most of their time in the quadrant itself, because the food will keep respawning and then its reward will keep stacking up. So the few times that it actually goes out, it will just like quickly go to the sleep sites and returns right back to the quadrant. Yep.
So can we go back to the slides, please?
Yep. Lost my slides. There we go. That is not what we want. Oh, I see. This is why we ask for some notice on this.
Yeah, sorry about that again.
Can you see anything? I can't see anything. No.
Yeah,
there we go. Okay, yeah, next slide, please. Yeah, so one of the key things that we learned when we were doing this was the importance of balancing the focus between network design and hyperparameters and the design of reward in the environment. Because early we put a lot of time into building the network for the baseline environment, but we found it wouldn't converge. And we decided we needed to build a simplistic environment with really basic rewards. And this acted like an overfit data set, so we could converge easily and debug the network. And that also brings me to the goal, the idea of goal-oriented rewards. So the agents optimize for whatever the reward is, and it's important that the reward represents the goal. For example, in the survival environment early on, we constrained sleep and food healths to each meet a minimum health level, but it made the agents only focus on one or the other. And when we changed the constraint to having an overall health, it made more creative strategies for the agents between replenishing food and sleep. In the future, we'd also like to explore other model architectures and investigate trading the model over a larger number of episodes, especially on some of our environments like the navigation one. And that's it.
All right. Thank you. It's interesting that you tried to go for something in reinforcement learning. And I hope that you learned a lot doing it. And I think that's a worthwhile exercise. I guess I didn't understand that you hadn't really identified a problem. You just sort of jumped into this agent game world. I thought there was a more specific problem that was being identified. Because I'm not sure what the actual problem is. It's somehow agents have to live? Can you give a definition of what problem is being solved by this RL algorithm?
Yeah, for sure. So the main goal of all the different environments that we were using was for us to be able to just observe whether we could make the agents act in creative and human-like ways. And so every single environment that we used had a different end goal, but all of them are based around human-like survival. So for example, in the survival environment, the agent's actual end goal is to maintain a health level that's higher than 50% by collecting food and resting and competing against the other agents when they're collecting the food.
That makes some sense to me. I would strongly urge when you write your report to put some clarity around that, because here's what's a little bit defocusing on and the way you talk about this is all about, this became too much about, here's how you do RL, and it's all RL specific, and it's about all the terminology, and it's not about solving the problem. And that is off topic of a key part of learning here. I wanted people to drive from the application itself, and maybe there's more evidence of that if you cast it that way, but I really got lost on that in this presentation because it was so specific to internal things in RL, and so it's hard to follow. Let me give you an example of, let's see, I guess none of your actual results you are on these slides. You showed something, and I don't even know what the context is. You showed the evolution of your agent's behavior over time.
Right.
Is that
correct?
Right?
Here's the link in the chat to where the demo is hosted, so you can check it out if you like.
But I want you to get clear on this question. I want your final report to get better on this. So your agent learned over time in one, but is that in one training session that you're representing there, that it gets better and better as you're training it, or is this over the progress of your project that it got better? Like, what is time when I'm watching just one of those things where you said, now you can see it's learning how to go inside the door, inside the barriers. What is time there? Right? What is happening over that time?
So pretty much, I guess to kind of define time. So I guess in the beginning, like a lot of we just kind of just like neural network training, like we just kind of threw together a neural network and then set some arbitrary reward, and then we wanted to just see what happened, right? And then like as we progressed
You
over
really
the
have to define that clearly. So that's one run over. Tell me how much time those things are taking. But one of those
so
things are
okay,
the
so so the good thing is that we can actually view the environment and how it's behaving like while it's training.
Can I get you to answer my question, please? The question was, for one of those videos that you showed, here's something change, here's behavior changing over time. How much time are we talking about? Actual
That
time?
was about like 40 to 50 minutes
40
on average.
and what is
Yeah.
being and the agent neural network
Hmm.
that's making decisions based on the behavior of the other things, that decision network is one of the things that's learning there.
Yeah, so the
Yes,
network is learning.
the answer is yes.
Yes, yes,
Yeah, it's good to
yes.
say yes if the answer is just yes. So but it's RL. So are other things adapting over that time, but beyond the internal neural network, or just the internal neural network?
So internal neural network is like just like a neural network. It's just the way that we're defining the labels and the way that we're training it is the reinforcement learning aspect. So the internal neural network is learning
Yes. Is anything
as it
else?
goes.
So yes. So the answer is yes. The internal neural network's learning. I think I got that in the previous
Yeah,
question.
yeah,
Is
yeah.
anything else adapting? Any of the other parameters adapting in that environment over that time?
No, the reward for the environment stays constant.
I see. Okay, so it's just the neural network. All
Yeah.
right. Um, okay. Ash, any comments?
It was good. It was quite ambitious. It's really good to hear folks learning a lot about reinforcement learning from here. My biggest comment is for certain sections, it felt like you kind of just not skimmed, but like ran over it really quickly. That it would have made it harder for the audience to understand. The data processing part was one in particular where I felt it was a bit really quick. And it was an integral part of the explanation. So in the report, just make sure that with the data collection part, because it involves a lot of discussion of states and rewards, and these are very RL specific concepts, it's going to be important to make sure that all of that is clearly explained and defined in that context. Otherwise, good job.
Yeah, I think it's a good point. The data collection, you said, there's no data to collect. You build an environment, but you got an environment, and so it'll be important to say, what did you do to change that system, Mujoko engine, like what to create the data that's being trained. So I understand and agree that you didn't have to collect data; you had to write code that generated data automatically. So you should be clear on what it is you actually added to the environment to do that. I don't see any of that here exactly. So is there anything you can add to say what code you created that?
Right. Yeah. So like in the original environment, so it's just basically as you probably know, the OpenAI hide and seek. So we based our environment off of that. Like our and essentially what we did is we defined the action space that our agent able to take. For example, in the XYZ direction, the agent can have different velocities along every direction. And then that's all, like that defines essentially the action space. And then in terms of the observation,
Interrupt and ask. So that's setting parameters in the environment. Is that correct?
and also like involving adjusting the actual environment, because in the original one they have like way more complex age. For example, they can rotate in like polar angles, for example. So we have to take all of that out, and then we have to adjust the internal action space that they define to fit our own purpose, because obviously like we wanted to like go for something that's like way simpler.
Yeah.
So yeah.
So fair enough. Make it clear both. So there you're saying what you changed.
Mhm.
Would like to know what, if it's a parameter, instead of 5 agents, you turn it down to 2, that's not too hard. But
Right.
if you defined a 3-dimensional or that's a 2-dimensional structure, that's a, wall, that doesn't strike me as too hard. But if you had to write code that is executed, then that's kind of relevant and is the equivalent of what everyone else is asked to do, which is bust their butts to produce some data. So make sure that's really clear in your final report. Any questions from other people?